So, I start? Oh.
It's not sharing anymore, Seogi. I'm looking at you, not your screen.
Screen share.
Oh, it changes when you plug in. I've had that issue before.
Sure. So now it works? Is it works?
Yeah, now it works.
So can I start?
Absolutely.
Okay. I'm not prepared, but yeah, I have some thoughts. So this is the presentation that I gave in AGU with Sungin and so his problem is like a dam monitoring. So here's our setup. We got this earth dam. The left side is the reservoir. So we have some like a hydraulic load, and then the other side is like there are some people leave, and so it's very important to know where there's a leakage or not, and all the like hydraulic heads should go down below the land. So that's the problem. And then the structure, they have a sand. So it's like it's not like a solid rock, but it, yeah.
But your computer has the ability to zoom.
Yes, I do.
Mac is special, but
so here's sand. So that's basically like a loose sand, and then there's a clay core. So clay core, like it's very impermeable, like the zone. So the hydraulic head will like drastically, like it kind of go down pretty quickly in this zone. So it's like having a really resistive layer or the resistive target in the DC problem. Anyway. So the motivation to use SP is something like that, because you can still use DC problem because it sees the conductivity contrast, and the water saturation, it will be different between like kind of this fully saturated zone and then dry zone. So if that like changes due to the leakage, using the DC, you can still see something. But still, that's not like a direct detection. So for instance, if you have a leakage here, only changes you can see is like this water height difference, because that changes the water saturation. But like sometimes fully, like water is saturated fully, but like it doesn't let you know how fast it moves. So how much leakage you have, it's kind of hard to see from the DC problem. If you want to see with the DC problem, you need huge leakage. So what's the alternative? So SP could be an alternative because it's more direct method. Because what it does, like so if there's a flow, that flow is like that's the source of the SP signal. So it's a little bit different from DC. Now you don't have any control source. You put the same like electrode arrays, but like this water flow generates the electrical signal because it moves the ions, and you can measure it on the surface. Yep.
So, like your red dashed line, that's the limit of your water saturation.
No, that's the like it's the water level. So okay. That's like will be a dry zone. This will be fully saturated.
What would it look like if there were no leakage?
It'll be like higher, I guess.
Okay.
Yeah.
Higher on the left.
Yeah.
Sorry.
Right. Yeah. Right. I think because it drops quickly. So, like if you don't have any liquid, it goes a little bit down like this.
And then the flow rate would be close to zero on that right side.
Exactly. Yeah. Okay. So this is sort of kind of conceptual model, and that's actually the fluid flow. This is the velocity of the fluid, and then this.
Like flow right at the top of your model. Yeah.
Pardon me?
Like you have that yellow bit right at the top. Yeah, where your cursor is.
Oh, like it's a little bit fake. So yeah.
How did you set up that model?
So I've set up a boundary condition at here, I put a Dirichlet, and then I put a Neumann until here, like all those boundaries. So there's a little bit of details because I had to define the boundary condition inside of your mesh. So I'm actually not solving like this part, but I'm only solving inside of your mesh.
So this is a tensor mesh?
Yeah, it's a
So
tensor
you're
mesh.
Basically zeroing out things.
Yeah, exactly. Yeah, exactly. Yeah, it's a little bit annoying. But
It's not necessarily wrong, though. I mean, it's not telling you the amount of water. It's just telling you if there was water, it would flow faster.
right. So yeah, here I think what I did is actually I solved this full domain, compute the pressure. Well, I actually solved for hydraulic head, and then you can compute the pressure by subtracting the height. Then you find like a zero contour. So I'm assuming above this one, it's zero pressure, meaning like there's nothing happening. But like, yeah, it's not quite right. Okay, so idea was actually like developing a simple outline tool because like source of DSP is the fluid like a fluid flow, and then we're getting the electrical signal. So you need this full like a software. You need some sort of fluid modeling that you can simply compute the hydraulic head or hydraulic velocity. Then that's your source of SP problem, use DC, and solve this SP. So that was the goal. And then at the end, you may want to recover some hydraulic parameters of the Earth that you can see fluid. So that was the goal. So the RC flow is basically DC equation, very similar, assuming the steady state. And one assumption that I made was K is not dependent upon the saturation or hydraulic head, which is not a very good idea. But like sometimes fine. I think this Earth dam example is not a very good example to do that, but I did. So I usually put the Dirichlet on each side, and then like for the top for the moment.
And when you say that, because your mesh is actually like the staircase.
Right.
So that's on these faces.
Yeah.
It's Neumann, and then these faces.
Right. So you need a little bit of kind of those types of like you need to think about that, and you need to like do this kind of things. I have a little bit of like utilities that does it. Yeah, it's just I don't know. I wasn't a big fan because like there's a better way. I either use like I don't know like a unstructured mesh or something like that, which is better. I didn't have it, so I had to do that. Yes, so there's details, and yes, it's a little bit annoying, but like if you see the end product, that's actually basically same as how you solve typical problem, like octree. So like how it looks like in your code, that's fairly similar. So
Do you render like air cells inactive, or is that triangular mesh that's all the cells that you have in the entire problem? So just curious how you organize it.
so I'm actually only solving inside of this like a blue line. So I'm not solving above. I generate the mesh,
Yeah.
but I don't like I just
Yes,
like
you render
cut
that
it
in.
off.
yeah, cut it off. But you need to be a little bit careful about the boundary condition when you're doing that, because you need to find all the corresponding like faces and then define your boundary condition. So yeah, so that's with BC. We solve it, and we can solve the RC problem, and you can compute the fluid velocity or hydraulic head, which will be the source of the SP problem. And well, then once you get the fluid like property, you need to solve DC problem. So we got like this steady state Maxwell's equation, really well. There's a little bit of difference. Now your total current is a summation of your streaming current plus conduction currents. So conduction currents is what we usually think DC currents. And we know like this should be continuous. So div J should be 0 if we don't have any like active source. So by taking div, and then we can have this equation. So div JS is equal to minus div JC is equal to minus div JS. That gives a little bit of physics because your direction of your conduction current is always opposite to your streaming current. So if the conduction current flows like that, but the streaming current flows the other way. Okay. If you want to know a little bit more of physics, there is like a full book like explaining why is that. But like that's sort of simple.
Sorry, can you run that by me again? The conduction current, when you say conduction current, that is like fluid, that's following the fluid flow.
No, the conduction current is actually moving charges, right?
Moving charges, yeah. So that would be due to the flow of water, right?
Yeah, well, like it's induced by this, but like it exists together coincidentally. But there's two different, like basically there are sort of different currents though, because the net current should be zero.
Right.
Like a div J is zero.
Right.
So there's two, there's conduction currents and also streaming currents exist.
One's like the flow of ions in the water, which is JS, and then one would have to be some movement of electrical charge that balances it.
Yeah, exactly. Okay. They're opposite. I think that's important to know. Then that is like this like a typical equation that we know. So like this JS is different from what we usually use as an active source, which is delta function. But yeah, anyway, you can use it as the same notation. Then basically that's the same DC equation. So now you need to know what is streaming currents. So we define streaming currents as like this. So it's like a different constitutive relationship. Here L is that's the key parameter, which is called cross-coupling coefficient. So it's actually how much electrical potential is generated due to the hydraulic head difference. So like it's delta phi divided by delta H. So, and then it's proportional to sigma. And there are a couple of different ways you can define that as like a hydraulic head or hydraulic velocity. So some there's different people use different terminologies, but at the end of the day, like that's basically the same equation with different terminologies. Okay.
So you don't have to differentiate between the conductivity of the earth material and the conductivity of the fluid that's moving. You just have
differentiate.
Yeah, so that sigma is all those things lumped together. Like it's taking into account conductivity of the fluid and
yeah, well, this is like a pretty nonlinear property, and then this is unknown. So like people, like even in lab scale, they were trying to know what is like L, and they were like doing some experiment. There are quite a few papers about like talking about that. Yeah. It's like a dump that there's all this like effect happening. Because if you think about that, that's pretty nonlinear, right? Yeah, because then also if you think back about the fluid problem, that was pretty nonlinear, and that nonlinearity actually propagates back to this L. So yeah, but like we're thinking about the problem is very simply, okay, let's say we know the L. So that's my assumption. So one interesting thing you can think about is like if you kind of like decompose this term, then you can break apart as two terms. So JS was like QV multiplied by U. Okay.
Sorry, what was QV again?
QV is like it's also it's excess of electrical charge per unit volume. So it's pretty similar to L, but like units is a little bit different.
So it's a charge density.
Sort of like how much charge is generated, I think, due to like water flow, I guess. Because like
how much charge is available to move.
Right. That's probably right. Yeah, exactly. And and then we know if you don't have any fluid source, divergence of U should be zero. So for instance, like this earth dam problem, except for your boundary, like U is always continuous. So that like is usually zero in our interest of domain. and like this will be 0. So you're only getting like what actually generates your signal is the difference of this QV in the domain. So if your material has different QV in the domain, that discontinuity actually generates the SP signal.
And so QV, it's not a material property now, right?
Yeah,
It's
not yeah, it's like it's like a
function of the dam, the amount of fluid,
right. Yes.
and okay.
Yeah. So that there needs to be that like a discontinuity of that property in the domain. So L is pretty similar to QV. Because like remember, L was QV multiplied by K, which is complicated. But at the end, the problem is pretty simple because now like here, our M is actually all in the right-hand side. Let's assume that sigma is known, okay? Which is not quite true, but like let's assume that we got the DC array, then we can get pretty good conductivity structure. So that's okay. Then you need to choose the model. Like here we have actually 3 choices. You can choose Q, which is like a divergence of JS. So it's like an electrode. So it's actually basically a source inversion problem. And or you can invert for JS, which is a vector. Yeah. Or you can invert for H, which is hydraulic head. Or also you can invert for velocity. Well, you have lots of choices. But here I'm considering 2 cases which is one is scalar Q and JS is the vector. So basically it's similar to mag inversion if you actually like linear mag inversion or MVI inversion if you take the analogy. But I'm not using integral equation but PDE to do that. So yeah, that's actually the equation. A phi is equal to Q. And then if you take the derivative, A is not dependent upon M. So we don't have that term, additional term, but like we're getting this. So depending upon what your choice of the model, this will be different. Okay, so we use SimPEG. And so here I'm showing the example. So this is a 3D model. That's a plan view at the like 39 meter below, and then this is 45 meter below. So this is 2 depth slice. So we have a 2 leakage path, and then that's a section view at here, and then this one is here. Okay, so we have a 2 leakage path, which is like 2 blocks in a half, not a half space, but like with a dike. And then I define like so first I need to solve the fluid like a Darcy problem. So I first simply define the Dirichlet at this end and that end.
So are we still in the jam?
Sort of. Like I'm not using yeah. Yeah, I'm like using just like a tensor.
If your dam is a cube.
Yeah.
Yeah. Imagine. Yeah, not very practical. Anyway, so I solve like a Darcy equation. So here's my boundary condition that I defined, and then here's the sort of fluid simulation result. So basically, it's actually solving DC problem then, but like with a different boundary condition. So you have 1 excitation. So here we have high hydraulic, not high hydraulic conductivity. Oh yeah, like high hydraulic conductivity at this leakage path. So fluid mostly flow here and then has a higher velocity, and you can see that. So basically it's have a conductive layer or conductive target. That's very similar. And then by using that, assuming you know the L or QV, right?
Yeah.
So you can compute the streaming current, which is like this. So yeah, you can imagine how hydraulic head looks like, or hydraulic gradient it looks like. So that's actually how the electrical field looks like, how the currents looks like. So yeah. So I was asking, what is the like? So I'm showing the streaming current. What is the direction of the conduction currents? And, okay.
So conduction current would be opposite to that.
Yeah. Yep.
Okay.
Yep. It's kind of hard to see, but anyway. Then by taking divergence, you can compute the Q, which is like a charges. So you have a minus charges and plus charges here. And then using that as a right-hand side, we can compute the synthetic SP data. So SP data usually have a one reference electrode and then just compute the difference. So it's like a pole response, similar. Because I'm not changing that reference electrode usually.
Can I think of the conduction current as like a secondary due to those charges, or is that backwards?
Well, like a conduction, like a streaming current, it's not. I think it's a little bit. It's a right-hand side. If you think about it, that's a right-hand side, and then that right-hand side is generating actually the conduction currents. So all physical things, what you probably think it's.
Okay,
So I think.
so the conduction current is actually due to like those charges building up.
Yeah, exactly. But the streaming current is more like a fluid flow. So if you actually invert for fluid, like, because direction of fluid flow will be similar to, it will be same, not same, but like that streaming current will probably a good kind of, it reflects how the fluid flow is happening in the earth.
Right.
So by inverting that, looking at that streaming current,
Yeah.
you have a good idea of what is flow in the ground.
Okay.
That's actually about the idea, I think.
Okay.
Because those charges are exactly what you expect for the DC case, right?
Right.
You get your current flowing from left to right. You have a more conductive body there. You get the positive charges on the right-hand faces and the negative charges on the left.
Yeah. Right. Exactly. So actually, if you think about a little bit differently, if you think all of this on the surfaces, then you're actually finding where your source is, right? Like, because that's what usually happens.
Right.
And then you can even like think about like the resolution might be not very high for in terms of depth because your excitation is so simple compared like similar to mag or gravity. So here's our inversion. So I like this invert this SP data. First invert for Q. This is the like a depth slice, and that's the cross sections. So I use the depth weighting. Otherwise, like my sensitivity is pretty high on the surface. And this is the current density. So this is amplitude. And
So in this one, you have two.
So basically, this is true model, and that's a true.
Okay.
And that's the recovery model.
Okay, so you have. Sorry, I thought we had two different models, but this is actually just two different slices through the same.
Yeah, exactly. Yeah. So this is all same model, but the two different slices. Because I was curious, like, oh, can I get depth information?
Yeah.
Because like I put a little bit different depth.
Yeah.
I think which is pretty hard target here. I think
Yeah.
the difference wasn't big. So I'm sort of like a little bit negative, not negative, like a little bit pessimistic result that, well, like it cannot distinguish this depth and that depth with DSP. What I hoped was actually in the beginning by using DOMs like this sparsity constraint, I'm still pretty sure I can get much better result, and then I think I'm pretty sure I can get the right depth here because if I'm pushing hard.
Yeah.
But somehow, like that performance is not great. I have a couple ideas why, and then I think our optimization need to be a little bit modified, I guess. Current one is actually like working for first order problem for very smooth inversion, I think. But for your sparse inversion, I don't know. I wasn't sure.
Here you said you're doing some sort of depth weighting.
Yeah, and that is also killing.
Are you updating?
Updating the depth weighting.
Or you sensitivity weighting? Are you updating?
No.
Yeah.
Yeah, so I think there are quite a couple like spices that I had to do, but in theory, I think.
That's a cool problem to test on. Yeah, sure.
Yeah, in theory, should work much better, and then you can probably like kind of get the good depth. And same as currents. So this is
Down,
right. Yeah. This is the current density and amplitude. It's a vector inversion. So if you look here, it's like it's kind of hard to see, but it's a vector. So it goes like kind of like this, and it goes like that, and that's a true, and that's recovered. So it does do an okay job, but it's still pretty smooth, and like getting a horizontal information is okay. Yeah, and then you may argue, oh, by looking at the data, I can still get the good horizontal location. Sure. I think this SP inversion needs more API information. Like either you need to know the depth, or you need to put some sparsity constraint. Other than that, like it's the amount of information that you can get from this inversion is not great, I guess. But I think still have a chance. Probably a little bit more interesting thing is how I implement it.
Where are you working right now, so?
Oh, this is not like in the main.
It's your personal brand?
Yeah, personal points. I in the SimPEG SP and SimPEG RC, but I did test, but like not seriously. So I might.
I just
yeah. So here, because I have a whole bunch of properties. So I'm separate. Like for instance, when I'm inverting for the vectors, I separate for x, y, and z direction, and either like q, h. What I hoped I can get the property in the source, because that was my initial plan. But because all things are actually happening in the source, so I hope that I can have a property in the source. I can pass the property map to the source, and then I can directly use there. That was what I hoped. I mean, I don't know what was the problem, but I have a little bit of problem, because I think that's probably keyword arguments, because that setting the keyword argument didn't set the mapping, I guess.
So right now the source doesn't inherit from the SimPEG property class.
Oh, I see.
So it doesn't trigger any of that stuff. But
Right.
Yeah, I think that would be the ideal way to do it.
Right. Yeah. So if you look at how I implement it, it's so basically what you need is eval, and then I have 3 different eval, and then eval derivative, it's the sensitivity. So yeah, if you want to invert for source, that's how you do it. And then actually I'm probably using just same JVAG in the DC problem, I guess. Maybe. Oh, maybe not. Oh, no, I don't. Oh, no, actually, maybe. Yeah. I think I'm using actually same JVAG, because like it has all the things, and so I don't need to do anything. And then because I had to do what I had to do was actually developing this part, and then plugging into the current DC problem, and then actually sort of works. Because this one actually inherits the DC problem. That probably was the reason why I did it. Yeah, it's kind of cool. Like sometimes, because like if there's a pretty general chunk, then you just need to inherit, and then like if that works for your problem, you can just use it. It's cool.
That's really cool.
Yeah, that's it.
Was it well received? People were.
Yeah, I think people were.
So what is like currently done in SP inversions, and like what's like leading practice there? Has SP been used for DEM?
Yeah, that has been used for them. And
Is that mostly by looking at the data?
No, I think they did invert. So I think this is sort of the cutting edge, like that's what they do. So that's sort of the 2 kind of state of art inversions. What they like
Is
people are.
ready for the scalar or the vector?
Yeah.
And what were Burke's comments? Because I know you had a good chat with him.
Well, like if you think about, I think here, like if you think about this right hand side, inverting for JS is like kind of hard. Like, because what your right hand side is divergence of JS.
Right.
Meaning
There's a
like,
null space.
yeah, there's a null space that you cannot like recover. Because so actually Q is that's about the information that you can get. And that was his comment basically. Like, so you cannot get like no more information by using JS.
Right.
But I don't know, because like that depends like upon like what your constraint of your inversion, because you can actually inject that information through your constraint, then basically like known is pretty similar. So I don't know, I wasn't like physically right, but like depending upon how you implement, it's different. And then especially current, if you invert for current, it's more like a direct. Oh, okay, that's how the current flow. So that's I thought that's okay, but having both is like I thought that's better because like depending upon your like problem, your interest, you could choose differently. And then I think SP is probably like widely used because like it's they are using for geothermal, and also this kind of earth dam example and what's that Kamini that they are using for like this like a little stream and then or something like that. So, and there are quite a few different sources. So there's a streaming, like a fluid flow may generate, and then chemical reaction also generates this.
Yeah.
So sometimes using for mining application. Right. Yeah. Right. So actually, Misam, he's like visiting here, and he was interested. Like, actually, he provided data.
Oh,
Looked at it, but he, yeah, he's a mine problem that like have some data. And Sangon has a geothermal problem. So actually, inverted, and yeah, we recovered some like a kind of. I think at one point I showed you guys.
Oh yeah.
Yeah, it's like it's coming out of like this fluid like coming from like thermal fluid coming from the earth, so we can invert for that.
Like convection.
Yeah, so there's and then like Dom's what was his name? Craig. Yeah, Crack. Like yeah. Yeah, I think because his problem is geothermal, so yeah, he's got data. So that's
nice.
Bit of potential. Yeah. Anyway, that's it. Yeah. So I hope I can test a little bit rigorously and then merge back to main branch.
Where are you? I'm trying to look for.
Oh, it's not. Yeah, it's local. It's completely local. Yeah, my like if you look at the dam geophysics, that what I was working with.
What's SimPEG version? Is there anything?
Oh yeah, it's oh no, what happened? Oh, that's fields. Oh, that's weird. That's interesting. I'm not sure.
Confidence. You just come out there with it.
Not really. Interesting. I don't know. It's been a while. But what I did was actually simply implementing kind of define the boundary condition and solve DC problem. That was it. And then have a little bit of utilities that you can define like different boundary conditions on different sides. That was it. Yeah, yeah. I hope that I could have a little bit more time that I can implement like a kind of like a non-linear hydraulic conductivity, so I can like still steady state, but like do sort of Jacobi iteration or something, so that like not assuming, but actually solve for the problem. But yeah, didn't happen. Maybe at one point. Yeah, good.
One of the questions is like for the geotherm or with SPS, what steps are there?
Geotherm?
Like for geothermal application with SP, what steps are there?
Oh, I don't know. I think that really depends, like, because like geothermal is sometimes a couple kilometers.
Yeah, that's why I'm surprised you for that application.
Yeah, I'm not sure how deep you can see with DSP. But I think that depends, because like sometimes if you have a pretty good fluid and that generates pretty high voltages, but the decays, so like it's 1 over R cubed, so it's not going to be like you may not see 1 kilometer depths, but I don't know, a couple hundred, sure.
Okay.
But I think it's same as gravity and Mach. So how deep you can see with the density. Because like sometimes actually people can see pretty dim. So I think that's the same, I guess, same issue, like how big scale you're talking. If you're sort of thinking about big scale, like fluid flow, and then that generates voltages, then probably you can see much deeper, like kilometer depths as well.
Seogi,
Oh, yeah, good need.
Yes, God.
in terms of the receivers, I mean, how does that affect your depth resolution or depth sensitivity?
Well, so like a receiver geometry or arrays.
Yeah.
You're asking? Well, like I think that like that doesn't help too much, because if you have a really fine scale features on the surface or like that, then having a dense receiver grid actually helps. But what you're seeing from the deep, like deep structure is pretty smooth signal. So I think you don't need that much like a receiver grid, like a very fine receiver grid. But yeah, definitely helps. But the increasing the receiver point doesn't help to get a depth resolution in SP problem.
Oh, your aperture though, right?
Right, like if you have a large area, that actually helps, because that sort of captures your like a full kind of anomaly.
Yeah.
Yeah, I think that's probably more important.
Oh, are you going to be able to sample on the water side? Or are you going to technically only sampling on the...
Not on the water side.
So technically
Although for DC problems, sometimes they get the data on the water. That's not too hard, because like you put electrodes on the water.
Yeah, good contact.
They have a good contact, so. But I don't know, like they usually do a permanent system for SP. So putting, yeah, I'm not sure. I haven't seen like.
They would probably corrode pretty quickly.
Right, that's true.
Probably, yeah.
That's true. That is true.
Yeah, running currents in seawater.
Yeah, I think they usually put on the crest side, which is not the water, like those part. That's what they are usually do, I think.
So your survey would be probably left-sided, right?
Right. But I hope they could do 3D, not a 2D, not a one line, at least couple lines. Then like actually just seeing the data will tell you quite a bit of things. Otherwise, like 2D, then it's too hard, I guess.
Mm-hmm.
Yeah, well, I guess last thing I wanted to just bring up was that dev pull request. Yeah, if we can try to get that in, like, and just whatever comments, like you don't have to go too in depth, just like if there's things that changed, if we've added, there's things that have been added, that would be great to have documented. And then I think, I don't know, going forward, maybe trying to do this more often so that we don't end up with a 13,000 line change. But I mean, that's okay. It's great. Things have gotten better. So
yeah, going back into it, there's a ton of stuff that's changed and upgraded. So it's fine. It's more stuff.
yeah,
So
cool. And it would be awesome to get this SP, like even just a pull request as is whenever you have a chance. Because I think that could be really helpful for getting properties injected like into the survey. So you can start thinking about inverting for sources like in a natural way.
Right.
So.
Right. Yeah, it sounds like we got all the pieces, and then it shouldn't be hard.
Yeah.
I guess.
Cool. Is there anything else you want to go over?
no.
Okay. Thanks, Seogi.
Thanks, guys.
See you, Goodney.
See you later. Thanks for this.